test. Hello, test. Hello, test. Hello, test.
Is anybody coming tonight?
Yeah, they're on their way.
Huh. Yeah, it is a little chillier here in our garage too. We've got this, we're both at 55 degrees.
Oh, here we are. I'm going to talk to that mic there.
How close should I stand?
No, that's fine.
Is
That's all I need.
That's loud enough?
Mm-hmm.
So do you have workstations for them, or each week it's a different location with a different project?
It's a different project, yeah. So we do have some of the,
So where's your project today?
we're going to talk about amps.
Operational amplifiers.
Yep. That's here.
I packed those. Well, I cut
Well,
them up and put them in smaller.
Yeah.
This is kind of what I feel like I'm doing nowadays.
That game.
Putting on weight.
Oh, it's a financial gain there, right?
I'm about eating too much comfort food.
Yes, it's going to be going in for that financial gain.
Yesterday was he had his best week ever in Alaska last week.
Oh, that's good.
Then yesterday he lost some, but today he made that up. So.
Well, that's.
I heard somebody just pull up.
19 below. 19 Alaskan degrees.
Well, when I checked our tree thermometer, you're checking your thermometer here? Because our tree thermometer said it was like -12.
Oh, okay. Oh. I'll check my tree thermometer.
We can read ours from
A
indoors.
treemometer.
Thermometer, yes, we can read ours from indoors, which is very nice. So we're also monitoring your garage temperature, our garage temperature.
You need some discs.
And what are these for?
I don't know.
What are they made of?
They're wood.
Oh, they're wood.
Make little ornaments or something on it. There you go. Ornaments.
How did they ever come up with that?
I don't know.
And gauges, the big
Yeah.
rings in the ears, those got pretty popular in Portland. It's like in Africa, you go, okay, that's what they wear. Oh, I think I told you, is this another one of those?
That's another one.
Okay. We were in, was it Kenya? I think so. One of the tribes there, they stretch earlobes out. And it's so funny because the men will wear their traditional skirts, but then they'll wear a sport coat over it when they're going to a job in the mountain city. So you see these skirts and the guys who have the earlobes, if they don't have a gauge in there, they're just these long, loose blue. And this one guy had it tied in knots. He tied it in knots so they wouldn't be.
Your ears tag low.
Yes, well, that's exactly what we used to joke about. So they would tie it like that to look more presentable and be safer in an office job type thing.
Well, it's highly up. The Korean people wear their tribal Korean things, and so they wear a jacket too.
Yeah.
They're around Westerners.
You definitely don't want your ears to get caught in the
Nope.
equipment there. So. But that's so weird to see somebody's earlobes tied.
Yeah. Oh, yes. So. Well, hello. Good. So far.
All right. Sorry about Tuesday.
This is James. This is my sister Jill, who's my able-bodied assistant here.
Nice. Yeah, we got called down to Chittenden.
Oh.
And then got hung up in Glen Allen because the storm was still going on and couldn't get through to Chittenden. So
You mean if you go to Chittenden for work? I thought that was all you did was fish there.
Yeah. Yeah, we've got sites everywhere.
Oh.
So every small community. So
Where do you work?
AT&T, Alaska. Yeah, so I do the long distance backhaul for all the local telephone services. So GCI, Copper Valley, Aztec, so
Oh my goodness.
yeah, they do all the local stuff and they tie it into our system to shoot the long distance back to the right picture perfects.
So you're on the road a lot?
Oh yeah. Yeah,
All
or
the
in the
time?
air. I fly like 3 times a week. So.
Are you a pilot?
No, I wish. Someday.
Someday?
Once I can, get me and the wife into a house and whatnot and take care of all the other priorities. Then I'll be able to spend money on things like a pilot license. But, yeah, no, there's, AT&T has 2 planes that they fly us around in sometimes when they decide they like us. Other times we just fly Wrights or Everett's, or Blues and whatnot. So, some of the sites, like we go to some of the military radar sites. Let's see, Indian Mountain's the one I've been to the most, but we've got a bunch of other ones.
Hill 3265, where.
Yeah, we got a
I
couple
actually
of them.
maintain that radar there.
Oh, did you?
Yeah.
Nice.
And, also, what's the other one on, Taylor Mountain?
I've heard of that one. I haven't been to that
It's
one.
right, right on the Canadian border.
Okay, yeah. Yeah, I know we go there, but I
You
haven't
can actually
personally
drive
been
there. But,
I've only been doing this for about a year,
Yeah.
but that's why I'm taking the classes. We don't do anything with radios, oddly enough, but they still want us to have all the certs, so we have to have the GROL to keep my job. So once I have this, I'm basically unfireable, which is awesome. But it's been, I tried doing the whole just take the test over and over again and memorize the answers, and got too much other stuff going on in the old brain. So
Yeah, we know what that's
small
like.
business owner and tech and all
What
that
did you
stuff,
do
so.
before your AT&T job?
So I bounced around a lot of different satellite jobs, mostly, or cable. I was a lead for GCI for a long time. I ran a crew here in town for the field services guys, so the actual installers. And then I was also the only GAF instructor, non-union GAF instructor in the interior. So I taught a lot of people how to climb telephone poles. And that was fun. I worked on the commercial side for a little while, and then I tried going to their travel group, because they have a group that handles a lot of village telephone services too, but they kept hiring people from down south, so I kind of got tired of being in the same position for years and years, so I jumped ship. Before that, I was a DirecTV tech, so did a lot of that.
Are you Alaska born and raised?
No, I'm from Kansas. So,
Kansas, okay.
yeah, I hail from the Great Plains, so but I have acclimated. I'm full Jeremiah Johnson now, so it's no, I came up in '09 with the Army, and just decided I loved it up here. So it's a lot different than Kansas up here. So
We just moved up here
You're
from
not
Oregon
Kansas
anymore.
anymore.
Yeah, we're not in Oregon anymore.
right. Yeah, that one, and my last name's Payne. So when you're in the military, and your last name's Payne. You do a major. Yeah,
I like that.
Yep. But yeah, and then I thought I was done with communications for a while there. So after GCI, because I left right when GCI got bought out by Liberty.
Oh,
And all
okay.
that stuff started happening. I kind of saw the writing on the wall and got out when the getting was good. So, which is good because 90% of the people I worked with got fired. So, yeah, they came in, they did all kinds of restructuring. 2 of the managers that had been there for over 20 years just walked into work one day and had an email in their inbox saying, your position no longer exists. So, and the buddy that took the management position, or supervisor position that I was up for, it was going to be him or I, and I decided to boogie. So he got the position, he got fired. Well, it wouldn't last as long as I take my job anyway, I guess. So, but then I decided to become an electrician for 4 years, got my German license, and got
Very
tired of that.
good.
So,
Yeah.
I wasn't really tired of it, but the pay wasn't as good as it could have been. shut down. So my buddy hit me up with AT&T. He said they're hiring, good work, they pay good, and so went back to communications. So,
Very good.
and here I am. So yeah, that's fun. And he's been warping my brain for the last 2 weeks, 3 weeks. So
Yeah.
but it is good. I understand a lot more about the low voltage stuff. So.
Well, let's see. Last Tuesday, we built some little amplifiers, and since nobody was here, I guess we could repeat that part.
Sure, yeah. Sure.
So,
You had one person here, right?
yeah.
And the weather, I guess people were concerned that the storm was coming a little sooner than it came. Because Tuesday it did start snowing. We got a couple inches, but I wouldn't have expected that to scare so many people away.
Right, especially in Alaska. You kind of get used to it after a while.
I know.
But
Yeah, no, for sure enough. I know Kevin, he had to use that down, he had a job to do.
gotcha.
And, Shariah, she's taking finals, so.
Oh, gotcha. I'll show you this.
Finals in what is she going?
She's civil engineering.
Civil
Oh,
engineering.
wow.
Huh.
This is what I was doing Tuesday.
Oh,
That's coming back around Black Rapids area.
yeah, you know, I was in Cheyenne, Wyoming, and we'll go over Happy Jack Pass between Cheyenne and Laramie is like that 80-mile-an-hour wind.
Yeah, it's just the road just completely disappears. It's crazy.
When I was coming back from Bible studies Monday night, it was snowing, and a rude truck, someone in a big pickup truck, pulled around on Farmer's
You
Loop,
got a white out.
and he went around me and pulled front and total whiteout.
Yeah.
I don't drive, that was,
When you do that, just take your foot off the gas and goes to a stop.
Yeah.
that's all I do. I took my foot off the gas and I was just waiting for him to pull ahead and for the snow to all.
A fair number of churches.
My buddy got in a totaled his truck. Some guy did that to him. It was a real bad snowstorm, but they were coming up that on-ramp from Pegger onto the Johansson, heading down towards Geist. And he's on that on-ramp section there, and same thing, some guy didn't like how slow he was going, so jetted around him. Well, it was actually a taxi driver jetted around him, and then ended up spinning out in front of him because the snow was so deep, and the car wasn't meant to go through the snow that deep, so same thing, total whiteout conditions, got in front of my buddy, and then lost control, started spinning, and my buddy just right into him, and
Two total cars.
No injuries, luckily.
Wow.
I mean, if my buddy had a little bit less self-control, I'm sure there would have been some injuries. I think his wife was in the truck with him. I guess he's pretty level-headed. So.
And then that truck, he ends up stopped at the stoplight, and I pulled right up behind him, so it's like he saved no time.
Yep.
So good. And as I go, hey, I'm driving cautiously, I'm below the speed limit on purpose because the snow's coming down and I can't see very well.
Yeah.
Oh, rude.
Yeah.
I thought everybody up here would be really good.
Oh, I am.
Most is the key word there. There's always a few, I guess. The bad thing about Fairbanks, since we have a college and 2 military bases, is it's always somebody's first winter. So yeah. There's always somebody who's not used to it.
So, are you going to be repeating that?
I will be repeating
okay.
Tuesday. So.
Perfect.
Yeah, so you won't miss out.
Right.
You do makeup classes?
I do, and Saturdays we're always available. So.
Okay. Gotcha.
He loves teaching, so it's like, avail yourself of his abilities and his knowledge.
Well, I very much appreciate it. The biggest problem I have with this whole class, or not class, but taking the test, is that most of it's French to me. So
When you take the exam?
I can pretty much take it whenever.
Yeah, I'm the sole proctor in Alaska for the GROL, so
Yeah.
I schedule on demand, you know. So.
Yeah.
Oh, that's nice.
No, I told him I was in a class, and whenever I
You just took a practice test. You have an active tip.
Not the full course, no, just a practice test, yeah. I've got the app on my phone,
Oh, okay.
so
Yeah.
whenever I'm flying somewhere or
Yeah.
something like that, I'll sit
Yeah.
around.
Well, let me know when you're ready and I'll set up there.
As soon as I pass the
They're
practice
kind of
test,
going
just
through
once.
a reorganization at the National Radio examiners, you know, so.
Oh, yeah,
That's actually good. We had new ownership.
gotcha.
The company that publishes this is they're moving over, moving to another company.
Oh, really? Okay, gotcha.
So you can proctor the exam when he
Yeah.
goes to take the official one?
Yeah. In fact, I have to, because I'm the only one in town. I'm the only one in the States right now. So.
Wow, yeah.
My brother's one of a kind in many
Yeah.
ways.
I'm special.
There you go.
You're spatial too.
Spatial, yes. Well, I could go through a course and then you get practice running the camera there, so.
Sure, yeah.
You're wanting me to learn
Now,
how
there's
to.
no zoom on there, you know, all you can do is
No.
about pan and tilt, you know, kind of keep it.
Okay. Oops. So leaving it here is the appropriate thing?
Yeah, that's just as good as anything.
And then I've got,
If I wander off too far.
okay, so show me what I can tilt without having this
Oh.
like fall off of the stand.
This loosens the vertical, just turn that
Okay.
knee up and down, and this tilts it.
And then does this loosen all?
Yeah.
Okay. I get,
So
okay.
you get a preview there.
Oh,
so.
there we go. Okay.
Well, there's a little bit of lag. Well, there's not much lag there on the actual YouTube on the web.
Yeah.
Okay.
Wait a second.
So,
Okay.
hi, welcome to General Radio Operator License. I'm Eric Nichols, KL7AJ, and I've been doing this for a while, so hope maybe some of you out in the audience are going to get something out of this too. Anyway, we spent the last couple of weeks here talking about the fundamentals, which are RLC, resistance, inductance, and capacitance. And these are the only real three components we have in all of electronics. And if you can understand these, you can pretty well understand almost anything we do here. Today we're going to go into what's called active devices, where these are actually variable values. But if you remember how we do impedances, R is resistance, and we have L, which is a frequency-dependent inductance or reactance, and we have X of C. And these both figure into this thing called reactance, either inductive or capacitive. These only subtract from each other. And we can continue on here, and we combine everything together, and we have this entity called C, which is impedance, or total impedance. So we understand these three and how they all interact. Anything we do from here is going to be a piece of cake. So we're going to talk about active devices today. So far, everything we've done has been passive. In other words, the components just sit there and run. They aren't adding any power. They aren't. All they can do is consume power. So we're going to talk about how we actually generate power, whether it's in low frequencies such as audio or radio frequencies. But we'll start with a couple of concepts here, and one of them is amplification. And I always like talking about vacuum tubes first because they're easy to understand. And the main users of vacuum tubes nowadays are high-powered radio and high-powered audio, like guitar amps and that sort of thing. So we still use a lot of tubes here. We have a tube over here. But talk about the fundamentals of how a tube works. So if we understand how a tube works, it's a lot easier to transition into transistors. If you try to explain transistors, which have some really bizarre physics involved, it's a lot harder. So we really don't need to know about the actual internal physics of a transistor. We just simply have to know how it behaves. So to understand the behavior of amplification, we'll go into vacuum tubes first. So go back 130 years or so, and we got this thing called a light bulb. And it's just the evacuated globe with a filament in there. And the filament in the light bulb is made out of tungsten, so we put electric current through it, and the tungsten gets very hot, and it use low white hot, or in case of what we normally use, we run it a dull red, cherry red to really dull red there for a specific reason. We aren't trying to generate a lot of light. What we're trying to do is take advantage of the heat. And when you heat up a filament hot enough, especially in a vacuum, it starts emitting electrons. So we start boiling off these electrons. And boiling is actually a very good term for it. So these electrons are now been ejected from the filament. Now what happens when the electrons get ejected from the filament, what's left behind is positive. We're shooting electrons off, so then we hit the material the filament's made out of, which is tungsten. The tungsten atoms now are missing electrons, and because of that, they're positive. So what happens is these electrons, rather than repelling themselves, which you kind of expect electrons to do since the old light charges repel, you'd think they'd want to all move as far away as they could and just accumulate at the outside of the envelope or the inside of the envelope, but they don't. They hang around this area here because this has a net positive charge. So these electrons here are just going to kind of form what's called electron cloud, obviously enough, or logically enough. And by itself, it's really not too terribly interesting. But Thomas Edison discovered, and what was happening on his early light bulbs, the filaments are evaporating and kind of eventually clouding out the inside of the bulb. So he tried all sorts of things to try to get rid of that. And he embedded a plate inside the tube here and put a small electric current on here. And lo and behold, he found out that electric current actually flowed through that external circuit. And so it was named the Edison effect. He didn't even bother to name it anything. He said he couldn't figure out how to make any money off it, so he lost interest so it just sat there for 20 years until somebody picked up on it. But it turns out that these electrons at this voltage here on between what is now called the plate and the cathode is enough to overcome the space charge, or this positive attraction here. These electrons can flow to here, and then they actually get reabsorbed into the plate here. And it's a very useful circuit. It's a one-way valve because the electrons cannot be forced back into the hot cathode. They can only flow in this direction. So in itself, it's a very useful device there for detecting radio. Of course, when it was first developed, nobody had any radio, so it doesn't have any use for it. But what we have here is the primary ingredient of all vacuum tubes, which is basically what we call a diode. It has two elements, two electrodes, and by itself it has tremendous use in everything from rectifying arc welders. You get DC out of AC. Anytime you need to convert AC into DC, we use a diode. Nowadays it's mainly done with solid state devices, but the vacuum tube is still going to be the main way of doing it for many, many decades. Well, along comes a gentleman by the name of Lee DeForest, and he discovered if you put another element in here, kind of a porous electrode, and you can actually see it in the tube there, this little spiral wound wire, and it's concentric inside the black plate there. And we apply a negative voltage to this. It doesn't have to be very much. You can actually control the electron flow coming through here. So what happens is we can use a very small voltage here to control a very large flow of electrons. So basically what you get here is a lot of leverage. You don't get something for nothing. You still have to put the power in to do something. But we can now control the flow of electrons with a very small voltage here. And that's where we get our basic amplification from. We're amplifying the control of the signal here into the rest circuit here. Well, one of the most fundamental uses of a vacuum tube is, by the way, this is called a triode now because we have three elements. We have the cathode, and the cathode sometimes designated K because, not because engineers can't spell, because C is already used. And then this is called the anode or the plate, and this is called the grid, and more specifically the control grid, because we do have some multi-gridded tubes that we'll talk about later. But basically, that's your fundamental amplifying device. Now, if we have a resistance in this plate here, what's the resistor do to current? It converts it into voltage. So E equals I times R, right? In the middle Ohm's law. So if we have certain value resistance and we have a varying current through that, it means we're going to have a varying voltage. Well, the useful function of this, if we put a signal into here, and we already talked about capacitors, how they pass AC, but they don't pass DC. What we can do is a very small alternating voltage here can become a very large alternating voltage here. And probably one of the more important things to remember is this signal coming out of here is always going to be out of phase with what we have going in. And that is because we can look at this tube as being a variable resistor. We have a resistance here, and we can put an arrow through. Remember, an arrow simply means that something's variable. Now, rather than have varying this potentiometer with like a potentiometer with a knob, this actually is the grid voltage, which makes the tube changes resistance. So the lower the value of resistance of the tube, in other words, the more current the tube has, the lower this voltage is going to be, because we now have a lower value of resistance, and this becomes a voltage divider. So again, Kirchhoff's voltage law applies perfectly here. So this is our fundamental vacuum tube amplifier, and that's as far as we really need to go on this now until we go into solid state, because 99% of what we're going to be doing is solid state devices. So, but the important thing isn't the physics involved inside here, but it's what the actual functionality is. So when we talk about a transistor, we don't have to know any of the solid state physics inside. We just have to know how it behaves looking from the outside. So we can treat a transistor as if it's a black box. Which is pretty good. Yeah. I won't go into all the evolution of the different previous configuration transistors. So most transistors now are what's called fused junction transistors, where you start with a block of semiconductor material, and silicon is the primary one we use now, although it's not the best by far. Silicon's very cheap, about 2/3 of the surface of the earth is made out of silicon. And it's good for pretty high temperatures, but it's by no means the fastest semiconductor in the world. There's a lot better materials for it. But since computers feed so much of it, it's become kind of the standard way of doing things. So we start with a block of silicon, which by itself, pure silicon is an insulator. It doesn't conduct any current at all. But what we can do is we can dope the material. So we put some of this few atoms, a very small number of some dopant material in there, usually a rare earth of some sort, that changes the characteristics of the silicon, which makes it either a P-type or an N-type. And so we use two different typing doping materials to determine whether it gives us some extra holes or we get extra electrons. Now, when we talk about a solid material, we don't have really, like holes of bubbles in there. What we have there is gaps in the valence electrons. So by putting a P-type material in there, we can actually have a surplus of, or we have a dearth of electrons, and we don't have these holes in there. We put a negative type material in there, then we now have some holes in there that the electrons from a previous atom can scoot into. If you remember our example of using a tube full of marbles and hammering on one end, we have this bucket brigade happening, so the electrons are transferred from one atom to the other, filling in the holes there. So if we can control where the holes are, we can control where the electrons flow. So we have two basic types of material, and most of the transistors we're going to be using are called NPN transistors, where we have a sandwich of two negative chunks of silicon, and these again, they're all fused together. It used to take three different types of material and weld them together or use point contacts. Nowadays, these are just infused. In the process of making it, they actually kind of stir in the dopant compounds they want. So what we really have here is two diodes back to back. And P-type material, you'll always have current flowing allowed to flow from a negative to a positive. You can't flow backwards. So a diode by itself, just two materials, is similar to a diode too. It can only pass current in one direction. So it's a rectifier itself. We have another junction this way. Now, what we want to do is we want to get current from here to here. So what happens is, if normally this junction here is reverse biased, if we put a positive voltage here, this is going to be backward, so no current's going to flow there. But if we put a small amount of current in here, what happens is this junction tends to go away. And as a matter of fact, this whole thing starts to look like an end junction. So then what happens is it becomes, it actually kind of combines all three parts of that transistor together. So now this becomes a partially conductive bar of silicon. That's an extremely simplified version of what's actually happening. But to understand what this actually does to the outside world, this is a pretty good example. What we have, just like in the tube, we have a variable resistance here. Either, if it's fully on, this thing acts like a full conductor, just acts like a piece of wire. If we have no current flowing between the negative and the positive here, then it's just like an open circuit. And then what we want to do is we want to find some happy medium in between where it's partially conducting, and then we can use it to control a large amount of current with a small amount of current. So this is a more of a physical layout of what's happening. What we want to do is now go is how do we fit that into a schematic. So simple for a transistor is this, and an NPN transistor, we have this arrow pointing outwards. We can also make a PNP transistor, which we'll talk about why it's nice to have both of them available. There is no vacuum tube equivalent of a PNP transistor, so we pretty much focus on the NPN until we get later on. We'll talk about complementary circuits, but for understanding the amplification, it's pretty simple here. So we have three elements now. So we have this thing called the emitter, which is equivalent to the cathode of a tube. We have this base, which is equivalent to the control grid. And then we have this collector, which is equivalent to the plate. So we have emitter, base, and collector. So most of the time what we're trying to do is control the current from ground, which is here. And we want to control the current that goes through our collector. And most of the time we'll have a load resistor here. We don't have to. There's cases where we just want a current amplifier. Well, hello, Archie.
Hello. Sorry.
No problem. We're doing review. So now we have this complete circuit here if the transistor is allowed to conduct. Now, ordinarily, if we don't have any voltage here, we have no current passing through here. But by putting a very small positive voltage on here, which that's one difference between that and a tube. In a tube, the tube is normally fully conducting unless we tell it to turn off. Transistor is normally off until you add a plus bias to the small bias voltage.
Take the inverted version.
Yes. So we have a small amount of current in here, and if we adjust this right, this amount of current here can set what we call the operating point, where we want, if we're trying to amplify an analog signal, we want this output to be able to swing both extremes. So we can adjust this bias voltage until this voltage here is half our supply voltage. If this is 12 volts here, we'll have 12 volts dropped across our load resistor, and another 12 volts dropped across here. That's the ideal, what we call the linear range. In other words, it'll act as an amplifier rather than a switch. Now, we'll go into digital circuitry later where we only use transistors either fully on or fully off. But for all the analog stuff we're going to be doing, we're going to be using transistor somewhere in between the two states. And that's where it amplifies. Now, the characteristic of the transistor, because of the physical dimensions built in there, a small amount of current here could cause a very large amount of current here. Same thing with a vacuum tube. So to change the gain of the transistor is it's called the alpha of the transistor, is the rate of the change of collector current for a given change of base current. So if we have a small change of 100th of a volt here, and we have this ends up with a whole volt here, we have 101 amplification factor. And that's the whole point of a transistor in the first place, is to amplify very weak
Voltage. Current or voltage?
Actually, both.
Oh.
It's current unless we have a load here. Now remember, if we put a resistor in there, the current change is going to translate into a voltage change. Because of our friend.
Yeah.
Okay. So, with that, any questions on that?
That actually makes sense.
So the next thing we're gonna do is we're going to build another amplifier, and Archie built 2 of them yesterday, but I pulled them apart so we could start over again.
Oh, boy. Figure out what was wrong with it?
No, but I think when
Okay.
when we had the power buses, kind of sharing each other, so we'll make sure that we only use a power bus for power.
Okay.
So, I'm pretty much gonna be done here, so Jill can spend some time looking at you guys putting this stuff together.
Oh, man.
Great.
We're now fully on YouTube, so you guys are gonna be stars here. So, let me draw the exact schematic that you're gonna build, and same thing we did last time, and you should have enough leftover parts there to do it, the roll.
Right.
There. Might have to measure them to make sure that you got them all right, so.
I believe it.
So we're gonna use a very, very simple, probably about the simplest possible voltage amplifier. So we're gonna have start with a transistor, and, looking at the transistor, it's kind of a half cylinder here, so looking from the bottom where the leads are coming out, it's always gonna be emitter, and here's your base, and here's your collector. So there's a little triangle there, look at the bottom of the transistor. Sometimes it's a triangle, sometimes it's a straight line, but the important thing is, keep the flat on the bottom, and then you can identify them.
Oh, flat on the bottom.
The flat on the bottom, yeah. Now, I was just gonna say, when in doubt, always check it.
Yeah.
Because matter of fact, I should probably print out a data sheet for those, because that's a good thing you want to get used to. So let me see what I've got here. Put that on the screen here. Yes, I can do that. Supposed to. And what type transistor are those? Can you see the type number on there?
2 volt 3804.
Oh, 2N3804. Okay.
Or 210, yeah.
Yeah, 2N3804. Okay.
Let's up at 9. Hold on a second. Old man goes.
If this is helpful,
There you go.
Oh, yeah.
there you go.
And then we still need to find.
Yeah. That's good.
Well, guess what? You were right. The round part needs to be down.
I think it's
I had it right
round
last
part
time.
down?
Yeah.
39.
You want to look at the flat part on the top.
Okay. And then it's,
Got it.
Okay, redraw your picture, Eric.
Yeah, I'll redraw the picture. So,
3904.
yeah, 3904. So flat on top. Emitter, base, collector.
It's so close to being wired from one side of the
And you'll need to put the camera back on for me.
Base, yeah, collector. Now, I think I mentioned that you can swap the collector and the emitter, and most transistors will kind of work. You know?
oh, okay.
Can you
But
activate?
you definitely wanna-
Selector, okay.
But if you have the base swapped with something, it's not going to work. So now we have a supply up here. Now, when
Eric?
you use the term VCC, which means common collector
The
voltage.
camera's not on.
Well, the camera's not on. Oh, it probably is. You just started.
You just switched to something
Okay.
else there. Hi, I'm Jill, his sister.
Hi,
There
Jill.
we go. We're on.
Thank you.
Okay. So, VCC, when you see it on, it means common collector voltage, which means if we have a transistor, a circuit with a whole bunch of transistors, they're all going to go to the same supply voltage, so we'll call that. So that's standard nomenclature. And sometimes ground is referred to as VEE for common emitter,
Oh,
or VCE, which is common emitter voltage. But everything we're doing so far is going to be just ground, so that's the negative terminal or supply here. This is going to be 1,000 ohms, and we're going to put a little resistor in here as well. And the reason we use that is for what we call thermal stabilization. Any transistor has what's called a negative temperature coefficient, which unlike wire, which as we know we heat it up, the resistance goes up. the resistance goes down with a transistor. So as the transistor gets hotter, the current increases, which causes it to get hotter, which causes the current to increase. So we can very quickly go into the state called thermal runaway, which we want to avoid. So this resistor in the emitter gives what's called negative feedback, and that prevents us from going to thermal runaway. Well, it gives us another very useful function here. It allows us to very accurately calculate the gain of a transistor, even if we don't know the transistor itself. And as it turns out, the gain of this amplifier is going to be the ratio, or going to be equal to the collector resistance over the emitter resistance. So in this case, it's going to be 10-1 voltage gain. So it's kind of neat. It kind of equalizes out the transistor. If you just tied this to ground, it would work, but then the gain would be entirely dependent on the gain of the transistor.
That's your range, though, right?
Well,
so
there's a certain range
that
there.
with your,
But by changing the ratio of these, we could change the gain of the transistor up to a certain point, and we got up to about 100-1 last time. So we'll play around with that again. Now we have to, one more missing ingredient is we need to apply a bias voltage on here. So what we're going to do is we're going to take a potentiometer here, and we're only going to use 2 legs of it. And so we're going to use our wiper here and come down to here. And what that's going to do is, this is a 20K potentiometer. So we can adjust that voltage. And the way we want to adjust it, until this voltage here is exactly half our supply voltage. That means the transistor, when it's actually amplifying an actual signal, you can go up or below 6 volts either way. And one other ingredient we need is so that we don't, so that our signal sources doesn't affect the bias itself. We're going to put capacitors here. Remember, the capacitor only passes AC, but leaves in all the DC stuff intact. So we don't want to do anything that's going to change any of the bias voltages or whatever. So by coupling capacitor, all we're going to couple through here is the signal. So when this is done here, we put a small signal here, a large signal here, out of phase. And that's about it. So Archie did this very successfully Tuesday night, so if you want to guide him through the construction of another one. And
again, that's the transmitter input, and then I guess we put out, that's output.
Yeah, input and output.
Signal.
Yep.
Input output. I guess.
Input and output.
What do you call it? Okay.
Okay. So let's build the circuit, and to avoid confusion here on this power bus. We use power bus. So use one side here. Will be negative on the left and positive on the right. So what we can do, we go right from here to the ground. Put it around here, and that'll tie all these to ground. And anytime you need B plus, you just go right here. So we don't have to use it.
So you want the right side to be the plus?
Let's see.
Or the left side?
The left side, maybe short.
Right.
More
And
short.
this one will be ground.
Yeah. So this is going to conduct clear buses as our bus. So this will be positive bus, negative bus, and then you can tap off there in many places.
That's a much better.
You got to work it anyway. So.
Yeah.
So I will leave you to your devices and let Bill practice his part of camera and getting all the interesting stuff there.
yeah.
You can scoot the camera closer.
Watch these guys get confused.
Check it out. We can always
It won't
test
break.
these guys. He suggested that we test these before we put them in.
Do you edit this before you put it on YouTube?
No, this is live.
Hi, everybody.
This is real.
I didn't even do my hair today.
Have you ever?
No, not like the last 4 years.
This is not a snowflake. This is not a snowflake class.
It is a snowflake state, though,
Yes.
as we're finding out this week.
Are we?
All the snows.
Oh, that's
We're being literal,
Yeah.
not figurative.
Oh, I don't have any. There should be black jumper wire. I don't know. Nobody makes black jumper wire.
All right, so you start doing like this. So we got one side positive, one side
Yeah, perfect.
ground. Okay.
Yep.
All right. So then,
Go off by 7.
said with the round side down.
Yes. Then that's,
Green is good for ground. Green is ground, right? We could get more.
Usually.
White, like the phone company, right? Black and red.
We're gonna want to tap off of that guy.
and again, just remembering, right, this is E, right, over
Oh.
here, and this is C.
That is B. Yep, that is.
C.
Yep.
So we want to take our power over to here, right?
Yep, trust but verify. Color
Yeah.
codes are going to be right, but I was like,
Yeah. Most of the time.
What are we looking for here? Well, I think these are going to be like hundreds. Let's find out.
and the little potentiometers are 20K. So
These tens? Okay, so we need to find something else. We want hundreds, right?
we want hundreds. Yeah. Now we did the second version. We did 10. Remember that?
We did, and then we got these out. Oh,
So there should be some hundreds still left in that
hundreds
pile over there.
Fine. Where do you, over here?
Over here, those are the ones we took out.
The blue ones?
These guys.
No, those are 20K.
Oh, these are 40.
You grab one of these or something. Let's see what this one is. Oh, those ones, the yellow. The yellow.
Remind me what a potentiometer is.
It's a resistor. It's a variable resistor. As far
Hot
as I
something.
know, it's a variable. Right, the potentiometer is a variable resistor.
Yeah.
Okay.
Essentially.
I think these are 100.
Yeah, maybe we put them away or.
Check these ones.
These are 1500.
Same thing.
Oh, these, let's see what these are.
Check those guys out.
Okay,
They might be.
perfect.
For the bigger leads are those 8-watt resistors. The leads are so thin they don't always make good contact. So that's why.
That's 100.
Oh, good.
Beautiful. Okay. So 100 right there. So around to
So we jump power over here, or can we use this to jump the power over?
we can do
Because
that.
it's coming off the power source, right?
It's coming off the ground. This is coming off the power source is up at top.
Power source.
VCC.
Okay.
Yeah.
So this would come off the ground side then.
Right.
We just put this down somewhere.
This whole thing is ground here, and this whole thing is plus. Pick one, anyone. You know, awesome.
Just get a little bit of separation there.
Let's see. Maybe 1,000 somewhere. These are.
These boards are pretty cool.
Is it?
Yeah.
Okay. Yeah, that's probably one we were using yesterday.
One
Mangled.
That's one of Heathkit's most famous products. Is these train
嗯
Oh yeah. That's 1,000. It's all mangled because we were using it yesterday. Hopefully it's still.
I got plenty of unmangled.
This is the
No,
one.
it's good. We're good.
This
and
is the one that comes off the power.
Off the power.
Okay.
Yeah.
And any of these things you're welcome to put in your own can there. And
Oh,
take
goody.
them. So, yes,
Oh.
it'll be-
That's nice.
Phone is coming out my ear, so I don't.
Do you?
We do have a few unusual ones. Resistors are cheap and plentiful, and they grow on trees.
Keep them. Yeah, that too. Yeah.
I think I've seen a resistor tree before.
And then also coming from the power, we'll have this guy. We don't have to put him on it. We can just kind of
Can we get these home and take them to Sean now?
Sure, absolutely.
Here. And this one needs a little
Well,
bit.
they don't get to take the blue boxes, they get to take all of it.
So,
Like, we could-
this comes
It's coming, yeah. You see where the,
Get you clear.
right,
This
it's
is-
also coming from the VCC
This is 12 volts.
12 volt. Yeah, oh, he's gonna get 12 volt
Yep, so 12 volt comes to this bar here,
and
so
then
this
we
jumps
need
it
to get
over
it
here
here.
into that guy.
Yeah, so we could like use
So
a
we're using
large
that guy,
double
not this
or
guy? Or the same thing, just two different kinds, or
not, well,
what is this thing? Little
they're
one.
like in parallel, so we're gonna use them both.
All those potentiometers are 20K.
20K.
Oh, I see.
See what I'm saying?
Yeah, so you're only gonna be using the center and, one of the outer pins on that.
Yeah.
The center pin's away, we'll leave one of the outside ones just floating.
Mm-hmm.
Okay. So then. At what point do we put this guy in?
Well, yeah, it's gonna go after this.
After that resistor?
Yeah.
The B leg?
Something that's less confusing, you put the transistor in very first, so then we can.
There we go.
Yeah.
And just put them in.
Yeah.
And just keep in mind
Yeah,
that's
that's
right. And then clean them.
Put a clean one, use that.
Oh,
If
right,
you want.
right, okay. And they're next to each other more.
Well, I usually, I leave one whole gap in between each leg there, this makes it a little easier.
Oh, do you, okay. Yeah, to see. And,
That makes
Get a
good
little
sense.
elbows in there. And push them all the way down, so. Contact. There you go.
Alright, so that's in now.
yeah.
And, sometimes it's a lot easier if
If
we,
we turn it around.
or, yeah, you do it that way.
Either way.
If you do it this way, then we can go by emitter base collector.
Okay.
Yeah, because you were saying with the round side down, right?
Right, but that means that like this is gonna have to cross over there, and this is gonna have to cross over to the other side. You know what I mean?
Oh, you're right.
Take a turn around, yeah.
You're right.
I mean, it's just visually easier, but
Yeah.
I mean,
Well, that's-
we could do it.
This,
We could do it. It's just-
When you start getting into radio frequency stuff.
Not the edge, because we're gonna have not quite the edge.
Yeah, put
I
it,
think, because I
put
think
it
we have
put it in the
something
middle
up.
there. I usually
Yeah.
put it right in the middle so you have a couple of views.
Yeah, so I think we have to put a capacitor somewhere.
Okay.
Now, when you start doing radio frequency stuff, it is important to not have things crossing each other, so. we'll
Oh.
talk about that.
Oh, right, yeah.
Wow. Yep.
That's where the people with the engineering degrees come in.
Mm-hmm.
All right, so now we've got that guy in there.
Well, good.
So then we've got to tie our voltage into it.
Yeah.
Okay, so you got, okay, you got your 12 volts into here,
Mhm.
and that needs to go to your collector.
B side or C,
It does.
which
Yeah.
that one is, yeah, C is on that side. So
Mhm.
let's use this little. That, right?
That looks good.
Okay.
Looks good. In there somewhere, we need a capacitor.
Yeah, you need to run a capacitor on the input and output.
Which capacitor are you using?
We can,
This guy.
no, you use one of the little guys, one of these guys here.
These guys.
And at this voltage, you don't have to worry about polarity.
Yeah, okay.
Okay. And that goes from the F flag to here, right?
That goes in between C and,
So you're gonna
that'll
want,
go.
yeah, you're gonna use a blank one for your in and out here, so you can jump across here if you just wanna have,
Right.
we can have our in and output signals.
oh, but the capacitor going out, did you want to do that first?
Yeah,
And
we can
does
do
it
it both, do it both, so
Do it
that
both,
we have
yeah.
to, so then we can have a convenient point to put our test signals there.
That's true, that's true. Yeah. Right.
two of these, don't we?
Yeah.
Okay.
And then actually we can leave the leg off, one of the legs off, right?
Do we leave one of them on?
Just to put, so we can put input, right? Input,
Yeah, so then you can put your, one side, you can just put a jumper. It's a lot, I find it's a lot easier if you have both legs tied down to something, and then
Oh,
for a test point, you just put a short
oh,
jumper on that side.
Okay.
that sounds good.
You know, they have a hard time making sure they kept contact, so by not having any stress on the component themselves when you're testing it.
And then just put, yeah, good call. Well,
Okay, so
Okay, so you got your 100 ohm, this is your 1K, and there's your 100 ohms, and you connect that to the emitter.
so we want to get
oh, yeah, that goes over there.
just like that. Okay, and then so we want to take this bad boy. And this goes to the middle leg, right?
Yeah.
Mm-hmm.
If it's too crowded in there, you can put it over here and use jumpers to get there, whatever. It's there, right on the side.
Or even, yeah, it could be over here. Yeah.
Because we want to leave the middle leg off, right?
No, the middle leg you need.
So it's just one of the.
One of the outer ones, you know. Yeah, that's good. Hang off the side there, that avoids the confusion.
Well,
These are, oh, you did spread them out. Okay, good.
Oh.
Yeah, the middles. So these are on two different buses here. Fine.
All right. Okay. So then one side of that needs to go to the middle.
Base.
Does it matter which leg of this I use?
No.
No.
If you're using all three, it would, but not.
Okay. And then actually, you know what? We could probably just go like, because we want to avoid crisscrossing so much. That's this guy right there. I have another one of these too.
Oh, that one's the ones.
You got plenty of wire there.
Can you tell if that's the same color? Or is that the same size?
This is all bent up. It's pushing into the.
Is that the 1K or the 100?
Probably
The 100 coming off the ground, yeah.
That's going to be one of the bigger blue ones, so,
Is it?
yeah.
Where did I put those?
Where did I put those?
Let's try that.
They'll grab it the hole a little better.
150? It's all good?
They should be all 100. We can get by with 150, but let me go see if it. Oh, wait, what do we got here?
150.
Let me get a.
What size is that? Does it look like any of these?
The same size roughly, but the stripes are a little different. Try to straighten this
You might test them out there. I
Okay.
think I got the 150 fixed in the 100. Oh, we haven't fun yet. The better camera, that'll be next.
Here's some
But
hundreds.
then we don't need this.
Did you get it, or did you want your fresh one?
This guy then, okay. I think I got it, it's got some resistance, it's not just pulling straight out.
It's
So
what we call a breadboard.
we'll keep this one, knowing where it is.
Yeah. Is that the one?
Yeah, that's the one, okay. Sorry, so now I just got rid of that jumper so we're not crisscrossing. So then for the other side, that guy,
Right.
we need to come off the 12 volt, right?
The 12 volt. Yeah, on one side. And cover it off the, one side of these.
Just for the sake of OCD.
That's right, OCD is good at it. You never heard.
So now I want to take off the, come off the 12 volts and go to that
Yeah.
middle leg, right?
Yeah.
And that's what's going to feed the voltage into that leg. Okay, so there. Come onto our power bus. Okay. So now we've got power comes into here, jumps over, comes through this guy, comes over here to ground. But from that, so from the other side of this leg, over here, we need to go to one of these capacitors, right?
From the base, the middle leg.
Yeah. The
See the middle leg?
one from the base and one from the collector.
Right, right, right.
Yeah. We're going to couple her in, put signal here.
That's right.
Couple her out.
So it could be the leg on the top leg. Middle and top.
This guy is going to go. Come on, man. Let's just say this guy. Or actually, let's do this here. Let's make that top leg. Take the long guy. Middle leg. That tie to this guy.
Yep.
Okay.
And let's see here. Yeah.
And then the other leg just goes to ground.
The other leg's
That's all it goes to.
The other leg is going to be, we're going to use our equipment here to kind of read it, to transmit it. So
Okay. That should be it then, huh?
Okay, so what we're going to do is you can have it over here so we can get
we'll turn around.
the test equipment on. We brought cookies. You guys got cookies just for throwing out there.
Oh, man.
Man.
Thank
Water.
Right.
Coffee.
You want coffee? Eric will have to
I'm
fix
just
the coffee.
kidding. I'm kidding.
He's been doing his coffee.
Yeah.
He knows how to get the coffee. So.
Mm-hmm.
Thank you very much.
Sure.
All righty.
So now we got a circuit that looks like it's ready to go. So back on the coffee break, we'll fire this thing up and see how little smoke comes out of it. We don't show anything big enough here to make smoke. that's the second half of the
That's what
quote.
my old journeyman used to tell me. The whole point of the electrical trade is just to keep the smoke and sparks inside the wire.
That's right. I'm gonna go fancy digital oscilloscope here, which is not very useful here. So what's really useful here is to have a couple of extra ground buses so we don't have all our leads connected. So I'll take a couple of short. Guys, since you got all this stuff, use that for connecting our test ground students. There. There. That is right. It gets really jammed up there. So here. We'll eventually use a second probe too, so around that as well. Yellow's channel 1, which is our, independent, what do you call it? Independent variable. So then, let's see. Input here. Base, okay. So what we can do is let's do a couple of convenient things here. Signal. A lot easier to connect probes. So I put a couple of extra convenient ground points here, so you don't have to cross it. And then here, this is going to be your input. Here's going to be your output. Should be. Let's see. Interface click. Oh no, this is okay. This is input. Okay, that's right. And the collector. Oh no, this capacitor needs to have that on the emitter should go 100 ohm to ground. Okay.
Top is collector, right? Top wire.
Yes. So top is collector.
So looking from this direction here, so this is collector this way. This one here is collector. And
Is it?
looking from the bottom there,
This
the
is
round
the flat. This is the flat spot. That should be the.
So you're looking at it with the wires.
Which way you look? Sorry, I know.
Well, here's a wire coming out, here's a rounded part.
Yes.
Here's
Yeah.
a basic collector.
Emitter.
So this is emitter, base, and collector. So the collector has 1K to why is that going around?
Because I had it the other way around. So I've got it.
Your collector needs to go to your positive supply.
Collector's on.
Here's your collector. Here's your 12 volts.
Right. We had it wrong on
Did we?
the diagram there. We were looking at it.
Actually,
So with it, I think we were looking at it from this side with the wires on top.
Oh, no, for the wire, you're looking at the wire side.
Yeah, so the easiest way to fix that then,
What did you do? We gotta turn it around?
just turn this thing around.
Sure.
Otherwise, we gotta rewire the whole thing. Then the base stays the same, we just flip the emitter and collector. Should have good contact on all of those. Alright, so now it should be right.
Collector is supposed to be with the larger resistor, though, right?
Yeah. There's a 1K.
We had it wired correctly, we just had
This
to.
is the emitter, though.
No?
That's the, yeah, this is the E. Wait,
No.
yeah, because the flat part is right here.
So we're looking for the bottom side here.
Okay.
Emitter, base collector.
Yes.
So your collector is 1,000 ohms, right?
This is 1,000 ohms.
Oh, okay. So you got your emitter.
We had it the right way. Pretty sure we was turning it around.
Emitter, okay. That's something that's not making sense here. Nope. Okay, so you look for the wire side. Okay.
Oh, from the wire side.
Yeah. Emitter base collector.
Okay.
From the wire.
Oh, okay, from the wire side. That's
Yeah.
right.
You may reinsert.
Okay. That's where I was wrong.
Always look for the bottom.
Okay. Yeah, okay. Emitter. Where's that connecting?
So 3 heads are better than 2, right? How special. No, you haven't done anything that total year yet. That big gray thing will. That's too close to the point.
Should be in all the right spots.
That's the emitter. Yep. Let's see, that's 1K there. So we don't, emitter
Oh,
is 100 ohm.
wow.
Do you need a magnifying glass?
Actually, looking from the wires, that's the collector. Collector's on the top now.
Round. You put it right down like that.
Where's the flat part? Okay, flat part's down, so we want to look at it that way.
Okay, so there's emitter.
Emitter, base, collector.
Okay,
Collector should be,
okay, so that's 100 ohm there.
that's on it.
Yeah. Oh, okay. Okay. Now that's okay. 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 Okay, now, when you apply the power, remember what was the first thing we did before we did anything else? We adjusted the bias until the collector voltage is 6 volts. So we're going to use a oscilloscope here, and we have 2 volts per unit, 2 volts per large unit.
Right.
And
Could we put just a wire up there, or what would we do? There you go, yeah.
Okay, so turn power on there. Okay. So we wanna adjust that pot till that comes into 3 units. That's 2 volts per unit. And that's a 10-turn pot, so you may have to crank a bit.
And then sometimes there's a delay. You can turn it the other way. See if that. Oh, I see something.
Ah,
I see it.
there we go.
Okay, down a little bit, it's gonna be on this,
Want to be right there.
right there.
Yeah.
Okay, cool.
Like right on the line.
Mm-hmm.
Okay,
Sweet.
now you want to put an input signal into your input, which is here. And, let's see, let's set,
That's good.
yeah, let's set that to, we don't need 5 volts here. Let's put the frequency down here, the kilocycle here. 1 kilocycle, and our amplitude, we'll put that up, okay, yeah. The voltmeter. Okay,
Just a little bit there.
just a little bit.
How do we decide on how many kilohertz or how many hertz?
Somewhere in the audio frequency range. Okay, so, let's see. Base. That's good. And you know that's not wired right, but it was actually functioning. So, bias is working.
Are we supposed to be connected up here?
No, right, but
No.
AC coupling here.
Uh-huh.
Sensitivity bit here. Let's see. One more signal here. Okay.
Very nice.
Yeah, it's not showing the gain that it's expecting. 15, and that's coming out that for you. That's what we want. Oh, there we go.
Also, I think our resistors, what else is going into the ground?
That goes into the emitter.
It's going to the other side here. I can't see what side it's on.
The right side.
It's on the ground side.
It's on the ground. It should be. Oh, it is on the ground. Oh, that's the 1,000.
No, it's 100.
Okay, very good.
We're really sure. Let's see. I'm gonna measure that again. Want to check that?
Sir. $100.
Let's use one of the blue ones.
Right.
Fat one,
100.
a little better contact there.
Yeah, it's 100. You want to use a blue one?
Yeah. Check one.
Yeah, good call. Good call.
These 8-watt resistors,
I did have
these are so skinny, they're
This one's 150. Let's try one of these over here.
I would say I did have to mangle that one a little bit to get it to go in there, so it might not have had good contact.
yeah.
100.
Okay.
What about these ones?
This right here is why you do the class in person.
Yeah.
Thank you very much.
You're welcome. hope you don't have a pecan allergy or anything.
You joker, you. Beat me to it.
That was cute.
Let's turn off the, it goes away. Okay.
I was doing something.
Okay. Sounds easy though. Okay. Let's look here instead. That's interesting. Let me use one of those 150 watts, even though they're not quite the right value.
Okay.
They
I wonder what's going on.
I think
This one
the
cuts
8-watt ones, they just are, the leads aren't
Yeah.
making contact.
Let's test this one. It's out already.
Yeah. 8-watt resistors are kind of unusual characters anyway, so.
150.
Okay.
Here.
That's a little more like it. Different frequency a bit. It's a little better. It's still not quite what I expect. So, I'm having to do some troubleshooting here. Okay, put the scope probe on the actual signal going in.
Okay.
We'll look at the signal going in.
Oh, okay, there we go.
We won't be using that.
We won't be using
Channels,
this.
not yet. They'll use the yellow scope probe. Move that to the
Oh, okay, this one is connected to, yeah. Okay, and this one.
Just leave the ground always connected there.
Ground, okay. Just connected here.
Yep. Okay, so that's about the input signal, so we aren't getting any gain, so go
We're
past the
not?
capacitor. The other side, yep. Yeah, that's good, okay.
Yeah. You just follow it.
Yeah, go to the base, go to the emitter.
Okay. That's going to be this side.
Okay, so we
Yeah.
got almost as much voltage plus emitter there.
Okay.
Let's see.
What about the base? You want to look at the base?
The base should be the same as here, but we can, if you can get to the base, yeah, measure it out, then just throw,
Can I get in the middle there?
You just throw a lead off.
That's true. How about that?
Close.
okay.
Looks good?
Yep.
Okay, getting off that.
Okay,
And then we're trying to read off of the,
let's replace
how
that,
about
let's replace, what's that?
How about here? Yeah. What about, here?
Yeah, what,
How's
so,
that? Really?
yeah, okay.
You want to replace the, transistor?
Well, we could do that, let's put a 10 ohm resistor in the emitter.
Okay. 10.
10, we're using that.
Maybe this
There's,
one.
second one there.
Is that that look
Look
like a
at these
10?
guys, I think those are 10s, those 10s.
I think you're right. Yeah.
Look at,
There you go.
it's almost a full voltage across the, yeah.
What we, let's see. Weren't the volts last time like 0.6?
Yeah, we use a lot less there, so, you know what, I think that transistor may be shot.
You think so?
Yeah.
Okay. Take it around the back.
Okay.
Oh, that's interesting looking.
Yeah.
Another transistor. Got one? Good.
I'll show you how to test a transistor. No
Oh,
millimeter.
yes. You want to try it?
Oh, sure.
Make sure you put that on the diode test.
This one. Yeah. So you just test the these on one of the sides. And it lets you know. Yeah, go for it.
So put their red on the base. You
Grab
got
on the
about
base.
6.6 volts between either two other sides. That's okay. No volts came to the other side.
These are short. Did you shoot? No, shoot. Let's go on for one side. What about the other?
Try another one there. Touch the probes together. Just make sure
Oh,
you-
yeah.
Okay.
There we go.
Okay.
Sweet. And what is that reading? That's
Well, it's actually reading forward voltage drop. That's each diode. Every diode has a certain voltage drop, and silicon is about 600 to 700.
Oh,
Germanium is about 0.2, or 2 volts.
wow.
So silicon has twice the voltage drop of germanium,
2 versus 6 to 700.
which is why for detecting radio, germanium is actually better than silicon. You need less signal to
Wow.
turn into it.
And you say 6 to 700 what? What's
No,
that?
it's millivolts. It's a voltage or a conductive. I'll show you how to test that with a scope there. It's kind of cool, actually. Okay.
New one is installed.
Okay.
Okay, so what we want to do here is we'll go back to DC and stick the probe on the collector again. And I'll make sure that we're going to turn on and make sure we got 6 volts here.
This probe?
Yeah. Yeah. Run this back to 2 volts per centimeter. Okay. And we'll drop this back down to 0. Okay. And then power it up, it should go to 6 volts. Oh, let's get this one. Okay. Okay, we need to readjust that now. We got a new transistor in there.
So Ray, just this guy?
Yeah.
stop at any point? Or
No.
Oh, it's not?
No.
Yeah, go this way. Drops. That's as high as it's gonna let me go.
Okay. Different pot in there.
Wanna try that one?
Oh, I'd love to try
Works the first time, it's, don't learn anything. Things
Right,
work the first time there, that's not supposed to happen.
that. Yeah.
never. Learning a lot of troubleshooting this time, which is good.
Okay, powered up.
Those are connected? Hold on. Is that connected in the right spot? Yeah.
Okay.
How is this
Mary-
connected? I don't know if is this connected to the potentiometer? Is it connected to,
Yeah, these two leads here, they're right next to each
I don't think it's connected.
Oh, you might move that one over, right? Make this red lead move it over.
One up,
One up.
just one up. This
There's,
one.
there's nothing on that.
Is there nothing on it?
No.
There's two wires here that come out of this.
Yeah, I lined them up with these wires.
Are they?
Sure this one's lined up.
You'd have to be really split open to do that. I guess you did, I don't know. These two?
Mm-hmm.
Yeah, you jumped to space? Okay.
Okay, look at the supply volt, see, you only got 12 volts there. Use a scope probe. Stick that on right on the supply volt, if you really have 12 volts there. Okay, you got that, okay. Now go out the other, that's right there, yep. Okay, that's good. And measure what that about there. Okay. Okay, I just want to make sure that, actually 12 volts, okay. Okay, push that pot again.
Oh, yeah. This guy.
Just back up to
Yeah, so leave that connected to the collector. And this pot.
We want to connect it to the base. Or does it matter?
It's just kind of odd, it's not doing anything.
Okay, let's see, we have a 10K resistor here. We have a 10K resistor. Oh, pull the pot completely out. See that goes up 12 volts. It should go right up to 12.
Put it up, okay.
Pull it out. There we go. There it is. Okay. So let's see. Let's try a.
Tested?
No, let's put a 10K resistor. It might be. Here's the key. Just put that momentarily put an 8K resistor between ground and the base. See if that drops down.
Okay. Did I do that right?
Yeah, I think so. Let's see.
Did I hit the middle?
Looks like it. Oh, wait, you got it on the wrong side here. Got to pause this. You're on the ground side here.
Ground and base, right?
You don't want, no, you want hot and base.
Oh, okay.
We're replacing, okay, it came down.
Oh, okay.
Okay. Okay.
It did. It did come down? Okay. Yeah.
Mhm.
So, let's see, I'm gonna, this one came, so it should measure by itself.
Oh, outside to outside?
That's so there's a 20 feet pot. So then, it's set to about the middle. Okay. So that's all the way up on the side.
Maybe you have the transistor on. Would it
No.
flow backwards? It wouldn't flow
No,
backwards.
because we were able to adjust the bias on it to start with, and we wouldn't have been able to do that if we're backwards.
So if it doesn't hit a hard stop, what happens? When
No,
it gets
it
to
just
the
goes
end?
off the end.
Okay. It doesn't like break anything or anything like that. It just kind of free spins and then goes back the other way when you turn it around.
Let's see if I got it.
We've got so many parts. You can have all the connections right, but if you have a defective part,
Mm-hmm.
These tweakers are a lot easier to keep on there. Have a
Mm-hmm.
recess so they don't slide out of there.
Oh, yeah. That's the good stuff.
Let's go to the other one's only up to 14. Okay. So
Right.
that's the,
Is that the culprit? Maybe?
yeah, probably. So we'll move this guy out of the way. That goes away. So let's identify that. Okay, now put that in there. You should
Right on.
put in there, it should not go up to the rails there. So we'll take this, put that one here. Okay, put in there. Okay, why is that going all the way to the rails of this? It makes no sense at all. Well, I put the 8K in there, it didn't do that. There's an 8K resistor here.
Oh, it's still in?
So there's 8K, so if I put that where that pot is, it should. It's a super high gain transistor. Okay, tell you what, let's use a pot there, and we'll put a 50K resistor in series with the pot.
We're gonna make it work. We're gonna power through this. How did that work last night? Are you using different pieces? It's the same. Are we supposed to be plugged in here, or do you unplug that on purpose?
For that,
Is it unplugged?
I have to do that, yeah.
You did? Oh.
Until you get the bias.
Right.
Oh, 40K, so what you want to do is put that in series with the pot. So right up here.
Into your drawing.
Series right up.
That's what we're going to do there. We're going to extend the range of that pot there.
Got it.
I think that transistor's just a really hot transistor.
Wow.
They might have been the other one, so. Ordinarily, we wouldn't need that much.
Oops.
I don't know, it's got some tools or something.
Yeah, I got tweezers and stuff. You get tweezers?
Fumble fingers.
Something else. Poke that in there.
Check this there. You know, we need to warn. We need to have more failure points than we need.
And is that going in the ground or the?
Should be, yeah.
I mean, it should be in the.
Oh, no, it should be in the
ground.
hot. It should be in the hot, yeah, because you're introducing voltage.
Okay.
Or did I? No,
No.
this is backwards.
Does it
Should
matter which way, it shouldn't
no,
matter which,
pot
okay.
shouldn't matter which way it is.
Oh, it's not like the middle is base and.
Okay. And let's see. Okay, now you should be able to twiddle that thing and see what happens.
And sometimes it took a few turns before it woke up.
I'm not sure which way you want to go on that. Might be off the ends and put it the other way.
doesn't like me.
Well, make sure it goes all the way to the top again. Yep. Okay, so it's a 40K. Let me put 100K there.
What was, yeah, maybe I'm off, but did it matter that the other day we were using 0.6 volts? I don't remember what that one is. Did it matter? It was 0.6 volts on it. Did we use that in this?
No, we didn't even measure it. So let's see. 100K.
Man, what else could it be?
There's a if I put that directly across there, it should not go to the sequence of the event. I can't believe it. I've never seen a transistor with that much gain before.
Use another one?
Well, no, it just means you have to design circuit a little bit different. I've never, I should not. Okay.
Not just a QC issue, you think?
I mean, it's a really good
Is it
transistor.
red for?
No, it's just a really good transistor.
Wow.
Okay, so let's see. We can go to. Anyway, let me try this. Let's see. Yeah. Okay, well, got enough skin on my body there. I should probably go to 1 million ohms, and that is strange. I've never.
Huh.
You know what we can do? Let's try it. Let's, yeah, okay, we can do that. Put the pot in there, but the third leg, tie it to ground.
Tie it to ground?
Yeah, it's not leaving us floating. We'll
Hmm.
make that back up.
Okay.
Tie this to ground.
Huh.
Let's try that.
Very nice. I mean, go use that one, but I know these are hard after they've been bent.
So then the center one, you're gonna, yeah, you want the center one to go to the base, center pin to base. Knock to one side and ground to the other. We'll force it to work. It'll be a little flaky, but.
Nice.
I'm a sucker for color codes.
That's good. That helps a lot.
A lot of stuff's been blown up by breaking.
By not having the right color.
Okay.
It's funny.
And
just a little blip. There we go.
Oh.
Oh, is that it? You're gonna give me? I think that's it.
Really?
That's as high as she goes.
Odd. Very, very odd.
Top to bottom, there's like 2-volt difference. We don't need to adjust the monitor?
No. Okay. Let's put 100K here. Leave that like it is, and we'll add a 100K resistor with it. But now it's just got a red wire, so we'll put a 100K resistor here.
Aha.
Is that this guy? Is that the 100K?
Uh,
A little big? That dinky dee?
don't know.
I only spent 2 weeks doing this on some circuit. So this is not unusual at all.
That's a 40K.
Yeah,
Are you still waiting for the part?
I got it. It's part of it. We'll just have to put it
I
back
mean,
together.
well, I could try it again. Which one was the 100K? Not this one? Not this
I
one?
don't think so, no.
This one?
I think this guy here.
This guy? Okay, that one.
Trust but verify.
I'll let you pick it up. Dropping it. Noise. 110K.
Okay.
Close enough.
Ish.
That's within the percentages, right?
This is where it plays down. Place that wire with that.
Replace this one?
Yep.
Oh, yeah? How are we looking?
It's moving.
Oh, look at that.
Oh, look at that.
Oh, that's.
Really?
Oh,
That's
man.
Keep going. Yay.
Oh, man.
Okay.
There it is.
Okay.
Why did they do that last night?
I don't know.
I don't know.
I might have been working with lane transistors before. Now I got one that actually works.
Aha.
So anyway, well, now I put a signal in the input. Put a signal in the input,
Okay.
which is this guy here. And then we look at the output, which is here. Oh wait, which is the input?
Going into the base?
Yeah.
This one.
Oh, there we go.
Beautiful.
Yay.
Hot, so we'll go to amplitude here. Way down.
Yeah.
There we go. Okay.
Yes.
So now what we want to do is we want to figure out the gain. So what we can do is we can go to channel 2. Okay. Compare the input and the output. AC. So this is put on the same scale here. And we'll look at the take the blue and look at the input. So then we're going to compare the two signals.
This guy.
Uh,
We want to check
right ground, connector ground. Okay, so the blue is your input signal. Now, if we increase the sensitivity, we should have a little bit more there, okay? Now, you notice it's out of phase.
Aha.
And the fuzz here, there's enough gain there, we're actually seeing the residual circuit noise.
Wow.
A transistor, because it's not at absolute zero, generates noise.
It does.
Yeah,
Wow.
so some of that may
Okay,
be
so
causing
what we
noise.
did
So,
is we attached it to the same place.
yeah, so we're comparing, we're seeing how much gain we're getting. So this is our input signal, which is down here in the millivolt lead. So what we can do is then we can increase the gain until we actually saturate the output.
I
So
thought we needed to connect that to the C.
here. Okay, so we go to the frequency where they kill 8 kilohertz.
Why don't we connect it to the?
Well, we want to see what the amp's actually doing. So we need to compare the input.
Put that at the
voltage.
collector?
Yeah, well, the collector, that's what the output is here. Well, the only difference is we have a capacitor there. So put it on the capacitor output.
Oh, okay.
Okay. Okay. So the input and output is out of phase as we said it would be, right?
Wow.
And
It's more than 90 degrees out of phase, though, isn't it?
no, so it's going to be 180.
I was gonna say that's 180 degrees.
Yeah.
Yeah. Oh, is that because we're doing double capacitor?
No, it's because as we increase the voltage here, this voltage is going to come down because this resistance is going down. So it's going to be exactly what I expected. This is a voltage divider between the transistor and the load up there.
Okay, gotcha.
So we have a gain of at least 101.
Wow. And we do that again by measuring.
The ratio of the voltage. So what we do is we set these amplitudes.
Oh yeah, that's okay.
Set the amplitudes the same there. About, and look, that's 2 volts here versus 50 millivolts.
Yeah, wow.
50 millivolts, 20 volts, so it's about 101 thing. Now, a little bit of distortion here. Now, if we drop it back to, put a 10 ohm resistor, put a 100 ohm resistor back in there, the gain will go down, but the distortion also goes down.
Oh,
so we have a 100 ohm resistor.
the distortion on this whole.
Yeah, see this, it's not quite
I
a
was
sine
saying,
wave.
yeah, you can see it just barely.
Yeah. You have to recognize a
I
sine wave
see.
there.
Do you want a 100 ohm?
Yeah, put a 100 ohm back in there.
Okay, let's find one. It was one of these small ones.
Or if you want to get really fancy, use the substitution box here, and then you just click in the resistance you want.
There you go.
That kind of stuff.
100 ohms right there.
Go ahead.
So I'm switching which one?
We're going to replace the 10 ohm resistor, which is,
Did we use a 10 ohm this time? I thought we used 100, or did we switch it out?
I think we're switching out.
Oh. That one? Yeah. Let me test that. That was a 10. I guess so.
And this one goes to
Ground.
Sure was.
Okay. So now we have quite a bit less gain there. There's also a little bit cleaner there. got 50 millivolts and 540 volts, which is what you expect at one gain.
10-1.
And one.
Yeah.
And if we run this up when we start saturating again, we go to the amplitude. And notice it stays pretty clean all the way up there
Yeah.
until we start saturating. This starting to flat top there.
Oh, I see.
Now, what we can do here.
Huh.
Drop that back on again. You can adjust the bias a little bit while it's operating. So if you wanted to, there's your twiddle stick. So watch what happens when you do that. Okay, so it's starting to flatten off now there.
That is.
Now, ideally, is you want it to start flattening off at the same part of the cycle there. Back off from being here a little bit. Okay, now you see, now I go overshot a little bit, and I'll go back the other way. So ideally, it's when they flatten off on the top and bottom, exactly the same point. Okay, that is your bias adjustment. Now you're truly a Class A amplifier, which means it's linear. Now, what's really cool here with this circuit, this function generator, what we do is we can run a ramp into here. So what we'll do is we'll change this wave, and we'll change it to this. Okay. Now, if that's perfectly straight, that means the amplifier is linear. There's no distortion. I see a very slight curvature to it.
You do? Okay. Oh, yeah.
But if those are perfectly straight, if those lines are straight, that means there's no harmonic distortion.
I mean, it's pretty close, but yeah, I see what you're saying. No harmonic distortion. Okay. So our input signal is different now? That's what I'm seeing? Or what is that?
Well, I changed the input to a triangle wave.
Just to try. Okay, gotcha.
That's square wave. Square wave. Now, another thing we can do, we can go to an XY plot. And what we do is we change the horizontal axis here to your input signal, and change the vertical axis to the output signal.
Oh.
And then the slope of the curve is your gain. So we can
Nice.
So we go to let's see, do this display format normal. So we'll go to XY display.
You need to get one of those so I can come over and borrow it.
So there you have an XY display.
Nice.
Now, what's really cool here. That's not right. So, why is the slope sloping downwards?
Gravity.
Yeah.
Why is it sloping downwards?
Yep.
Because voltage drop.
Because input and output are out of phase. If you're in phase, it's non-inverting, it would slope up this way.
So it's just the way that's just the way it displays
Well,
the.
you're showing the collector voltage on a Class A amplifier, the input and output signal is always going to be 180 degrees out of phase.
And that's what that.
That's
Yeah.
what's showing. Now see where it's just starting curve there?
Yes.
That's where the distortion is happening.
Oh.
So if you want to play with the bias there, again, you can see what that does.
Okay.
Go ahead and twiddle the bias and take a look.
Aha.
See?
Really?
And that's just about perfect there.
And where do you want to be? You want to be right
You want to
there?
go as straight as it can be.
Right there. So what I see is it just going up and down. Like
That's
that.
just
Was it curving?
That's just changing a little bit of DC voltage. So you aren't worried about the actual position, but you don't want any curve. You want that as straight as possible.
Was it curving? Oh, it is
Yeah.
curving. Yeah, I see. Where are you seeing?
And that's why it's called linear. It's a linear amplification, which means that input and output are a straight line. So. Isn't that cool?
Is that about straight?
Yeah. So if I increase the gain here to saturate this, start doing some radical stuff there. Start getting distortion. Pretty slick, huh?
Yes.
Normal format.
Now the bottom of it.
Yeah, but just a little bit, yeah.
Just a little bit.
So what helps me remember things is practical application, like a field of work.
Sure.
So like, where would this apply?
Well, if they're doing an audio amplifier, in some ways, hey, this thing's distorted all like crazy, you know, well, that's to it, and you can find out, hey, is it linear or not, you know?
And then tune
Yeah.
your line amp.
Yeah.
So, okay. So I've definitely used line amps before.
Well, you know, all the guitar amps, you have voltage amplifiers to start with, then you have current amplifiers at the end there. High power stuff, but you don't have much voltage gain, so. And most of them are push-pull amplifiers, so a lot more efficient. You actually have two transistors, one amplifying the positive half of the cycle, one amplifying the negative half. And what it does, each one only gets a rest in between cycles, so you get a whole lot more power out without melting things down.
Wow.
So each half of the amplifier only does half of it.
Half.
Yeah.
Hey, there's a transistor in there.
So the maximum theoretical efficiency you can get on a Class A amplifier is 25%. They can never get more than 25% efficiency out, which means if you want 100 watts out, you have to put 400 watts in. that's theoretical. And,
Right.
that's,
But even
quite a bit below
practical,
that.
it's going to be
It's gonna be
much
less,
below.
yeah.
What do you think?
So
50% of that? 50% of
maybe,
that?
well, you can probably approach 25%, but
Oh, you could?
yeah.
Oh, okay.
But in a push-pull amplifier, you can get 60% efficiency. They're
Rest is
resting.
25.
They're sitting there resting half the time.
Half the time.
Do all amplifiers have transistors?
No, all these guitar amps.
I mean, besides the past tubes that have transistors,
No, they're still making all the. Yeah,
But
all your
that's
high-end,
using
all the high-end
tubes?
Fender amps, yeah, these are all tube.
I thought that was just the.
So the tube is our.
No, they like the sound of the tubes. When you
The
pull
tube
it
is
back,
our
yeah.
transistors.
Yeah, you pay a real premium for tube amps, yeah.
Yeah.
I didn't know.
Well, now you know.
Now I know.
Now, when a tube does distort it, it has a very different character. When you run a transistor and you run it to distort, it just clips.
So a
Where a
transistor.
tube, it kind of gives a soft, so that's what we're doing, the bluesy sound.
Oh, okay.
Interesting. Like you got it to work.
Yeah, that'll work, yeah.
So do you guys understand all the changes he was making to make it work?
I understand the change, but I don't know why. I don't know why. Do you know why?
Well,
It just
normally,
balancing would be my guess.
normally with like, 20K resistance, that's all you need to run this thing into Class A to get the bias at the midpoint here. The transistor had so much gain here that when I wet my fingers there, I just measured resistance when my body was about a mega ohm from my fingers, so.
That's what I kind of guessed you were doing, was tuning to an unknown variable, basically.
So by grounding the bottom end, that gave us more range to work with, than
Okay.
the 100K resistor. That prevents you from loading this down. If I put that assuming that this had to be way down near the bottom, like maybe 15K on the top and 5 at the bottom, that means this would be only looking between 5K to ground, which would load down your input signal quite a bit. We want this input impedance to be as high as possible.
Oh, you do?
Yeah.
Otherwise,
Otherwise, because remember the RC time constant, you're trying to pass the lowest frequencies possible. If this resistance is too low, you'll lose all your low frequencies because you have too much drop through the capacitor. So that's RC time constant. So
Okay.
the lowest frequency this will pass is going to be the inverse of the RC time constant. So I think this is a 1 microfarad capacitor, and you can figure out if this is like 5,000 ohms. The RC time constant, the 1 microfarad times 5,000, it'd be about, it would start rolling off or below about 1,000 hertz. Now, if we start lowering the frequency till everything starts dropping off, we can
Right.
figure out where the volume is.
Ah, we could have done that.
Yeah, we can do that right here. So we'll go back to sine wave.
Okay.
And what we do is we take a mid frequency where we're at it. And
We're at 1,000 right now.
so we'll run this up to full scale. And what we do is we'll reduce the frequency, drops off to 0.707. That's what we call our cutoff frequency.
0.707.
So actually, if you were measuring power, it would be exactly half power. So you aren't measuring power directly or what's against voltage. So if I decrease the frequency here, then amplitude will start dropping off at some point. This isn't too bad, actually. It's starting to drop off. So about 10 hertz it starts dying.
But if we, okay, I see.
So if you wanted to increase a
Took
bottom
out
end, if you wanted to, like, it's either increase that, but generally what you would do if you wanted to increase the lower frequency, you put a larger coupling capacitor in. So that our RC time constant is larger. And you can see where it was on top end. We got the 5 megahertz on here. Yeah.
Mm-hmm.
See what this does with the increasing frequency here. So find out where it starts dying.
So that's lowering, but then,
That's
yeah,
lowering.
high side, what, did we affect the high side by?
That should
resistance?
not, what we did should not affect the high side, but
Oh,
we,
okay.
we'll find out where it is here. There's 1.6 megahertz. Okay.
Yeah.
What about same frequency though? It starts
Is it?
about 5
Yeah.
megahertz starts rolling out.
Mm-hmm.
So you can go into low radio frequencies of that as well. So.
Wow.
Now, one thing on any amplifier, as you increase the gain, the high frequency starts rolling off faster. So we're running a very high gain here. If you're running back, go up to about 100 to 1 gain there.
Right.
The high frequencies would not be start blowing.
It wouldn't be,
fast.
okay, it might be at 3
Yeah.
megahertz or whatever, or less.
Yeah.
Okay. Ah,
It's called a gain bandwidth product.
interesting.
Figure of merit for any amplifier. Primary, you see it more on transistor amplifiers. There is an equivalent for the back and forth, but it's not as well defined.
And what was that constant over there you were talking about? The what?
The RC time constant.
RC time
Yeah,
constant.
we were doing that, charging a capacitor and discharging it.
Yes.
And it discharges every time you get to 60 or 37% of the original value and keep dropping down there.
Yes.
So the frequency response, or the cutoff frequency of filter, is the reciprocal of the RC time constant. So the shorter drive RC time constant, the higher the cutoff frequency is.
I remember that.
So let's see what time we got here. Enough time to.
It's 8:16.
Okay, well, we can go back to what I was going to do here. So now you know how an amplifier works, okay? That's pretty much the same. So we'll go into the next step there, where you don't have to worry about biasing and everything. We're going to talk about op amps. And nice thing about an op amp, everything we did here is all internal. You don't have to play with it. So you need to know what biasing is, so to know what they did when they built it. So using integrated circuit amps, you can get to to, bypass all that internal stuff. So the general symbol for this is a universal symbol for an amplifier. And here's some 741 op amps. These are the most popular op amps out there. They have about 30 transistors in each one. That first came out when I was a sophomore in high school. I remember the big deal. Electronic instructors said, look at these things, the whole operational amplifier, these chips, they're $7.50 a pop. And they're about 40 cents now.
Now? Wow. Oh, one question. Yesterday we were going to put that in series.
Cascade.
We're going to cascade.
Yeah.
And that was going to increase our gain.
Gained by the product of the gains of each one. So if we had 10-1, yeah, we have 10-1 gain and 10-1 on the other 5-1 gain.
And so that would affect the higher level frequency that we.
Well, that's not frequency, it's just how much voltage gain you can get for a given signal.
Right.
Remember, taking a typical radio signal, you're down there in the femtowatts, that very attentive intervals, you got to get up to where you can hear, So a typical, just a standard off-the-shelf AM radio has an overall gain of about 70 dB or 10 million to 1. So to get the power level of the speaker is about 10 million times the power that's actually coming in on the antenna. So. And that's a rotary-mill receiver. That's not a communications-grade receiver at all. It's just standard old off-the-shelf table radio.
Yeah. Wow.
So anyway, this is a universal symbol for an amplifier. Now, an op amp is a special type of amp where it has some, remember you always said we talk about the ideal first before we talk about so we start with this block diagram, and an op amp has 4 main characteristics. One, it has infinite gain, infinite voltage gain. It has infinite bandwidth, meaning it'll work from DC to daylight. In other words, there's no frequency limitation. It has infinite input impedance.
Infinite input.
Yep, input Z. And we have 0 output impedance. Okay.
Input impedance.
Oh, yeah, 0 output impedance. Now remember, when we built these amplifiers, we assumed the gain was a proportion of the output impedance, or output resistance. Remember, we had the collector resistance, and it was the ratio of the collector resistance to their emitter resistance. Okay. Now, what we have to do on this case is we have to modify this a little bit, but not too much. So what we do is we start with a amplifier which has all these characteristics. But we obviously, in the real world, you can't get those. So what we have to do is we modify this by external circuitry. And so when we have an op amp, we have the gain is determined by the outside components, just like we have here. This resistor would be equivalent to this resistor, which is called your feedback resistor, and their input resistance is going to be here. Now, you start with this infinite gain block, and then what we do is by adding 2 resistors here, we'll call this R2 and R1. And we'll talk about what that is in a bit.
And that was a.
But the voltage gain is equal to minus R2 over R1. Okay? So it's a ratio of those 2 resistors, just like it is over here. Okay?
What did you call R2 resistor? It's
Feedback.
Feedback.
Feedback resistor. Okay? Now, why is there a minus sign here?
Because voltage gain is
demonstrate with when you were using a sawtooth wave and showing the slope, and the slope downwards,
Right.
because this is inverting, okay? So the output signal is going to be
Oh, yeah.
out of phase with the input signal.
I see.
Well, that gives us minus sign, so it's going to be the algebraic
Opposite.
opposite.
Wow. I like how that works. Okay.
Nothing to it, okay? So, we can put signals into the non-inverting input, and we will talk later on about doing that, but this is a lot easier to analyze. The math is a little bit easier when we start using non-inverting inputs. We have some interesting situations. Another thing that's really neat about this is we put a variable resistor here. And let's say that resistor goes between 0 and some value, 0 and 100 kilo ohms, let's say. We can reduce the output level to nothing by turning that resistor down, bringing that resistance down to nothing. You have 100% in negative feedback. You can't do that with a non-inverting amplifier. The most you can get is 1-to-1 gain, which means you can drop it down so you have the same input and output. But here you can drop the output level absolutely 0. So all your mixers there with all the multiple sliders actually have inverting amplifiers already. So you slide it down, you're changing this resistance here, and bring her down. Yeah, absolutely. Okay.
It's a resistor, huh?
Yep. Your pots, your slide pots.
It's a variable resistor, or what do you call it?
Variable resistor, yeah, a potentiometer. You know. Same thing as your blue thing tip.
And that's with an inverting,
Inverting op amp, right?
meaning,
Meaning
it's out of phase
Out of
when it
phase,
comes-
yes, input
okay.
and output out of phase.
and then there's a non-inverting.
Yeah.
Okay, but we haven't talked about
We
it.
haven't talked about it.
Okay.
So, actually, the inverting op amp is a lot more common because it's stable. If any tendency to feedback is already taken care of because you're already using negative feedback. So when you go to positive, you have to be really careful about not oscillating. Now, you can use an op amp as an oscillator, and we'll talk about oscillators here, but in general, no. So now that we know how simple this is, we can make an amp that really works, that you don't have to play around with anything. Now, the only thing that's missing here is you usually run these on a plus and minus voltage. So we'll do a plus 12 and minus 12. And if we go to the we have enough time to yes, we have a half hour, so the last thing we'll build an op amp.
Plus 12 and minus 12 volts.
Minus 12 volts, yeah. These are designed to do that, plus minus 12 volts. So, we have a nice handy dandy.
I wonder where that is.
Maybe what that is.
Plus and minus, there's a
Well,
reason.
that allows to be DC coupled, and if you're amplifying DC voltages, you only want to be positive or negative. So you're going to the speaker. So what we have here, here's the amplifier with showing this power supply that's connected here. And what we're going to do here, and these are designed so you put your op amp in here and it straddles this thing here. So you have your plus and minus supply.
Yes.
And the pinout on any operational amplifier, just about any IC, is unlike transistor where you look from the bottom. These you look from the top and you go counterclockwise from the index. And that's a little tube of.
This right here?
Yeah. No.
Okay.
So we've got a bunch of 741s here. Bunch of 741s.
Okay.
So identifying, see there's a little dot there.
When I put my glasses on, I will.
There's a little dot in the lower left corner.
Okay.
And you go counterclockwise from there.
Ah,
Okay,
okay.
1, 2, 3, 4, 5, 6, 7, 8.
Excellent.
Okay, so we can pop this thing in here.
sides too.
So then here's your pin numbers, okay?
Okay.
And this is what we use. So offset null we don't use at all, so pin 1 is unused. Inverting input is number 2, okay? Non-inverting input is number 3, which will go to ground.
That goes around, okay.
But not to negative, okay? You have two polarities. You have a minus polarity and you have ground and a positive polarity.
Right.
So the non-inverting input will go to ground. The V minus will go to our minus 12 volts. The plus 7, pin 7 is a positive 12 volts. And pin 5 is not used.
Okay.
And
6 is output.
yeah, so we're only using 5 pins. So offset null, 8 is not used, and 5 is not used. So 1 to 5 are not used, 8 is not used. 7 is your positive supply, and the output is in pin 6.
Yeah.
So we will build this thing just like that, okay? And we'll use same values here. So we'll use 1K here, or 1,000 ohms here, and
Do 100?
oh, no,
Okay.
we use 100 here, and I'll use 1,000 here. And
Oh, 100 there? Okay. And so
Should we
that is active inside.
actually, but that's going to be, let's do it this way. You're going to have negative gain there, which it'll work, no problem. So use 1,000 here. You know,
Do you understand how what we learned before
so
ties into that?
so the gain is proportional R2 over R1. So that's going to be 10 more gain.
Oh, okay.
Okay. And so here's
So there's transistors in that, and there's something.
yeah, I got
that's-
here's the whole schematic.
Really? Wow.
But here's the actual schematic. And you can build out the discrete components if you want.
How does that compare to what we did earlier?
We have one transistor. This has 30.
There you go. So they're cascading.
Yeah, that's how you approach the infinite gain.
There you go. Just it's easy as that, bro.
Yeah.
Come on.
Oh,
Yeah.
okay. Let me number the pins here for you.
Excellent.
Here.
Ah. I like how. So it's just like what we just built, but 30 of them. Pretty sweet. In a small
The nice thing
space.
about op amps, you don't have to know any of the internal guts, right?
You don't have to.
You don't have to. All you need to know is external connection. So,
Yeah.
this is pin 7.
Okay.
This is pin 4. This is pin 2.
2.
That is pin 3. That is 6. That's it.
Input?
Input, we're
Oh,
going to use
resistor.
inverting input, which is
Oh, 2. 2, yeah. And,
okay. So, go ahead and build one. Maybe you can do this guy here. And,
1, 2, 3, 4, 5. Yeah, that's right.
have at it.
Okay.
Half an hour. Half an hour.
Half an hour?
Half an hour.
Excellent.
I shall return.
Well, it's easy to plug in the power stuff first, right? Is it? Yeah. Brown. Should we like brown? To be brown? Brown?
Brown or green?
Brown or okay.
Green is the official color.
Is
but
it?
Yeah.
Oh, well, our greens are really short
Yeah, that's what I've been using.
here. Yeah. Let's see if brown is. Brown. Yeah. And we want that to be 3. Okay, so we just, where's the dot. Okay, the dots appear. 1, 2, 3. Yes. 2. Well, let's do 4 and 7. So.
4 is your negative voltage.
Yep. Just make. Oh. And then 7 will go to the positive. Sweet. Alright. And, okay, I guess that just leaves us with 6 as our output. We'll just put a wire there because we're going to take a reading from that, right?
That is correct.
Okay.
Now, if you notice, in one way regard, that's simpler to circle before. There's a couple of components that are missing on that were on our single transistor.
Yes.
And what are those?
Such as
Well,
um,
what is not on here?
capacitors.
Very good.
And why is
That's
that?
why.
Are they inside?
Because we got a bipolar power supply. We don't have to isolate the DC voltage because if everything's
Oh.
working right, this is going to be 0 volts.
Okay.
That's why you use bipolar supplies for op amps. Plus, if you need a measure like you're using for instrumentation or measure a DC voltage, you need
Yeah.
to measure both high and low, right?
Yes.
You
Yeah.
put an oscilloscope there. That's all op amps.
So do we just need jumpers up 2 and 3 then? Or no, 3.
We're already hooked up on 3. We're already on the ground.
Yeah.
We just need 2.
You got minus 12. That's right.
Negative voltage lower.
You got 12 volts to 7. Okay. And we still have the 2 resistors.
We need our resistors.
We need our resistors.
Oh, yeah. Okay. So.
1,000 ohms here.
Oh, yeah.
And 100 ohms there.
And it should connect into the output. Okay. Resistors. Just loud. Let's try to remember which ones are which here. Are these 100? No matter how much coffee I drink, I always sleep like a baby after these class. Here's 100. My brain is fried. 1,000.
100 goes to the
From 2.
negative voltage.
Or just
No,
from 2.
negative inverting input
Connection point 2.
to, this is our input right here. That's our signal generator.
It is. Okay, excellent.
Let's go to our oscilloscope.
Oh, that's 1,000. Come on. Come on.
Yeah, you can reuse components. They don't
Oh.
run out of resistance. Have a fixed amount of resistance. Runs out of resistance with you.
Why don't we do that? Why don't we rip that out of there? This one? That's 1,000. Okay. So that needs to connect Ah,
6.
2 and 6.
2 and 6.
Yeah. So let's put this back a little. Like, let's put this here. And then we'll put, I'll get it. Is that 2?